In high school biology, many of us were taught that genes are something that you're born with and that don't change throughout your lifetime. Well, it turns out that's not quite true. We'll talk about that today. In 2000, scientists at Duke University conducted a study on mice, and they found something that greatly changed how we see genetics. They found that they could change the physical appearance of a litter of mice depending on what they fed the mom. If they fed the mom a healthy diet, the litter of mice was born small and brown. If they fed the mom an unhealthy diet, the litter of mice was born large and yellow, as you can see in the picture. And they could reverse this from one generation to the next. The important thing is that the genes were the same for both the small brown mice and the large yellow mice. So if both sets of mice had the same genetic sequence, why did they look different? Your DNA consists of a helix, and the helix is two intertwined sequences of data. Every cell in your body has the complete blueprint of you. It has the complete DNA sequence of how to make you. But not all cells in your body use the same sequences of DNA. How does one cell type extract different information from the DNA strand than another cell type does? A helpful example may be to think of bookmarkers. DNA basically contains recipes for protein. You'll have one marker where the protein recipe begins and another marker where the protein recipe ends. But those markers are not fixed. They can move. The process by which different segments of DNA are turned on or off is called methylation. We won't go into methylation in detail today, but it'll become important in future videos. The interesting thing, though, is that methylation can happen throughout your life. Between November of 1944 and spring of 1945, there was a famine in Holland. It was at the end of World War II, and families were eating 60 or 70% less than they normally would. They were eating grass, they were eating tulip bulbs, they were eating anything they could get their hands on. Scientists knew with reasonable accuracy when this famine began and when it ended. Using this information, they evaluated the babies of women who became pregnant during the famine. The first surprise was that birth weight of infants was influenced depending on whether the mom became pregnant at the beginning or at the end of the famine. If the mother was well fed at the beginning of the pregnancy and the famine happened during the last part of her pregnancy, the baby's birth weight was smaller. Whereas if a mother became pregnant during the famine and was well fed toward the end of her pregnancy, then the baby caught up and was born at a somewhat normal birth weight. The second surprise was those smaller babies who experienced the famine during later trimesters remained small throughout their life. Scientists conducted a long-term health study of people born in a small Swedish town between 1890 and 1920. The people they studied were affected by periods of feast and famine. And they found that the feast or famine didn't just impact the people living at the time, but it had a measurable impact on their grandchildren. They could tell by looking at the grandchildren whether the grandparents had experienced feast or famine. In all of the examples that we've talked about so far, the DNA sequence has not changed. The only thing that has changed is which part of the DNA strand is active and used for making protein. Interesting thing that they found. We've known for a long time that when a mother smoked, it had a detrimental effect on her baby. But what about the dad? They found that the babies of non-smoking women who had one-night stands with smokers had epigenetic changes to their DNA. In other words, different segments of their DNA were active than babies whose fathers were non-smokers. So even if the father was not around and the mother never inhaled a whiff of smoke, the fact that the father was a smoker still had an epigenetic impact on the baby. And it can skip generations, because baby girls form their eggs before they are born while they are living inside their mother or inside the grandmother. So it's possible for epigenetic changes to persist for several generations. Also, as we'll talk about in another video, these epigenetic changes don't only happen in response to extreme situations. They're always happening. So what would happen if the methylation process, that is the process by which your DNA strands are bookmarked so you know what proteins to make, what would happen if that were to somehow become compromised? We'll talk about that in an upcoming video. Today we introduced the concept of epigenetics, which is that the active portion of your DNA strand changes throughout your life. In fact, is changing continuously through a process called methylation. We learned that the decisions that you make can have an epigenetic impact not only on you, but also on your children and grandchildren. We'll talk more about this later, especially about methylation. You want to click subscribe and also click that little bell so that you'll know when future videos come out. Thank you so much for watching.